pushes it down and depresses it. Well, as that ice melts, what is no longer there? The rock is still there, but the downward force is not. So what does the rock start to do? It starts to come back up. And in fact, this is where those, you guys know I'm not a big fan of super environmentalism, especially when you don't look at the big picture. Okay. Right now, today, we hear in the Great Lakes about how much the Great Lakes are losing their water and how it's going to dry up in just 30 years. Okay, whatever. Completely makes sense if you think about it. Because what happened at one point is the glaciers kept it down here. Now, as the glacier started to recede from this land, what did it start to do? It starts to lift up. So what does that do to the water line down towards the north? Yeah, it basically raises the water line. Kind of think about it like this, because all that water is draining in. So imagine all this water draining in through Chicago, filling up Lake Michigan, and it's going to fill up and have a higher lake shore, basically in the northern regions. And then as that ice continues to melt, we keep getting this lift up and up and up, right? Well, now we basically had no more ice sheets, and so what's happening on this end? It's starting to lift up. What's that going to do to the water level? What is it going to appear to look like? No.
It's not going to split the water.
It's not going to split. What it's literally doing is it's going up. If this was your original water line here,
so in the southern regions,
southern regions are going to get a little bit more water, and the northern regions are going to look like it's losing water. Because you'll see just like your rings around your tub, so you guys might have some water lines on your tub, you're going to get water lines in the bedrock all around the shores of Lake Michigan, Lake Huron, and Lake Erie, and Lake Superior. But as that northern region starts to rebound, that ring starts growing up out of the water because the water is just draining downhill. And that's for the isostatic rebound. So if you talk to a lot of people about Great Lakes ecology, they're very concerned about the water levels because one of the fastest regions to be losing water right now is in the Traverse City area. And I laugh every time I hear that. I'm like, of course it is. Where else is it going to be losing the most? If we're really losing water that much out of the lakes, it should be lost at a uniform rate. Everywhere should be decreasing by the same amount every single year. You shouldn't have one location that somehow is losing its water at a much faster pace than somewhere else on the lake. It just doesn't work that way. So that loss that we're seeing is due to the isostatic rebound, and it's only an appearance. So that's what you guys, again, you gotta know your science. Because otherwise you will be bamboozled. You gotta know the science. Don't just be there to be the Kool-Aid drinker. And you don't know what that means, you need to go do your history. Okay? You gotta know the stuff. So that's one of those things, like I said, you gotta know. I've said this before multiple times in this class. The rocks tell you everything you need to know. The rocks will tell you more than any animal, any plant, any water system. The rocks will tell you everything you need to know. If you want to know what the environment was like 100 million years ago, go to the rocks. It will tell you everything you need to know. All right, so we talk about forces, or the stresses. Now I want to talk about fault systems.
would you want stress or
Shear,
shear?
it's basically being pushed and pulled in two different directions. They're literally being forced past one another. When we look at faults, faults are actually kind of cool. Again, this is on a localized region. Okay? These are not massive geologic features. These are very, very small geologically. And we have three types of faults. We have reverse, normal, and strike slope. Those are your three types of faults. Reverse, normal, and strike slope. And reverse and normal are really kind of difficult to identify, but the hardest part that you had is almost from your perspective. And that's why there's sometimes hard to differentiate between normal and reverse. And there's some small things that you can look at that, I'll kind of show you guys that allows us to see that. Now, one of the things that we keep in mind with the faults is that each fault is a direct result of the type of stress that is applied. And that's what I really want you guys to take out of today's lesson, is matching up the stress with the force that with the fault that it creates. So the first one here is a reverse fault. And reverse fault is from a compression force. So as those two blocks of land are being squeezed, we'll get this thing called a hanging wall versus the foot wall. Again, we'll go back to our blocks of land. As I push these together, what starts to happen? Okay, so this one drops, and this one starts going up. Do you see why we call it the hanging wall? Okay, it's literally just hanging off the edge. Okay, you guys see that? Call this the foot wall because it's the one that drops. Now, look at the shape of the hanging wall. Which way is it leaning? It's leaning forward. Okay, that's what tells you it's a reverse fault. We call this piece of land right here, call it a fault scarp. S-C-A-R-P, fault scarp. So that exposed rock surface right here along the what we call the fault plane, we call that a fault scarp. How many guys have heard the term the Niagara Escarpment? You guys heard that before?
Is that where it's pushed back?
No, that's just due to erosion. The Niagara Escarpment is basically this gigantic circle that comes all the way out from the eastern side of Lake Superior all the way down through Niagara Falls and back down through, almost back down to Lake Erie. And what that really is, guys, I want you to think about this. What's sitting right here on top? What do you guys see here? What kind of juice? It's a river. Okay? Nice and flowing, nice and simple, right? And when that goes up, what happens to my river? What did I just create? Waterfall. Create a waterfall. Most, not all, most of your waterfalls, especially what we would consider to be the most magnificent waterfalls, the largest waterfalls in the world, are due to fault plains. The Niagara River, which creates Niagara Falls, is a fault plain. And that's how we get that nice rounded edge. That horseshoe-shaped Niagara Falls is basically the fault line, and it sheared off, basically fell down, and that's how you start getting the waterfall. We look at Victoria Falls, we look at Angel Falls, those are all examples of fault plains that have created some of the most majestic waterfalls in the world. Not to mention Yosemite Falls. Okay. You guys see any pictures of that one? You guys gotta get out of the air once in a while. You guys give you a laptop so you don't ever leave town. Okay, Yosemite Falls is part of Yosemite National Park. Gorgeous falls. I'm going to tell you no more than that, but you should go look up some pictures. It's awesome. Okay, now a normal fault, okay, so I said, right? Reverse is from compression, being squeezed up. On a normal fault, what you have is tension. And so as I release that tension, what happens? It's falling down. So now our hanging wall is no longer being forced up, it's literally being dropped down. Notice right here, your escarpment, which way is it facing now? It's slanting back, okay? So that's how you tell the difference between reverse and normal. In reverse, that escarpment is going to be angled forward, and normal, it's angled back. So normal is with tension. So we'll see that here, where that hanging wall is being dropped down. And then again, we get this little piece of escarpment right there. All right, the last type of fault is a strike slip. And on this one, we're literally just sliding past one another. So your strike slip faults is a shear stress where you're sliding past one another. Yes, Brandon.
I don't know if we watched a video here or if I was watching it at home on the Science Channel, but I think it said something about California's doing the same thing.
California, okay. California is a transform boundary where you had two plates that are sliding past one another. Within that, you have this Honduras fault line. That is, again, a strike slip fault where you have the two pieces of blocks of land that are sliding past one another.
So that is the same.
It is the same. But when we look at a transform boundary is really a network of strike slip faults that basically outline the entire boundary. That makes sense? Okay. Then we have some interesting pictures for you guys to take a look at. You guys always want to know, okay, what does this actually look like in the real world? Here's a perfect example. If you ever go driving around anywhere where you have mountains or hills, take the time and look at the road cuts. You will be surprised at the geology that you find just from being on the road. There's a ton of stuff. Right here's a perfect example of a road cut, and what was unearthed here is a reverse fault. And you can see where the brown layer should have sat right here. So it's been forced upward, and you can get that angled forward escarpment sitting right here.
You know, I wonder what it's
I had no idea what this rock sign. And then in a normal, you can see how all these layers are slightly dropped down a little, because right here, match this one with that one, so it's being dropped down a little bit. But again, it's all in the angle that you see here. So notice that we're angled back rather than angled forward. And then the last one, this is actually kind of the cool one, strike slip. And strike slips are kind of cool. They're really, from aerial views, they're really easy to identify. And that's just basically, you can see here where this is an orange tree grove. You can see how you have these nice, perfect lines. All of a sudden, this bottom part's been shifted over. Same thing here with the field. It's been shifted over. And so those are some common examples that you'll see, especially out of Southern California. Yes.
Why is it just right there where the trees are? It shows that it is.
Because that's the most obvious to look, but what it's really doing is extending all the way through.
Well, because you can't see how the road, though, up there.
Yeah, you're not going to see it in dirt on dirt. You know, it's not really going to see it. So, again, same thing here with these roads. It keeps going beyond the image. So, if we kept planting more trees here, you could see the offset there. In fact, and we might watch this video at some point, but literally, there is an image after the 1906 San Francisco earthquake where they had a picket fence that outlined somebody's yard, and one portion of the fence had moved back 6 feet. Or they just broke the fence and just moved it back. So it's kind of cool. You know, a lot of times these things lay dormant and you don't see any evidence of it at all. And then when it finally hits, you start seeing this line. You can start connecting the dots and actually see where the whole fault line is, which is how they actually came to find the fault line. All right, so that's it.